In this next video, we're going to take a break from fractions and look at dividing polynomials. Now, I say we're taking a break from fractions, we're really not. When we're looking at a fraction, this is a division problem. That's what a fraction bar represents. But every example we've seen up to this point, we've dealt with these rational expressions, and our main goal was to simplify them. In this video, what we're going to do is see how we actually divide them. So what do we get when we divide the denominator into the numerator, and is there stuff left over? So we're going to look at two different techniques for dividing polynomials. We're going to look at long division and synthetic division. Long division, you guys are probably thinking, I remember this from back in elementary school when we were using that division bar. And the beauty of long division of polynomials is that it's exactly the same. So we're actually going to open up with some basic long division problems. 723 divided by 5. We remember how to set this up. We've got 5 on the outside of our division bar and 723 underneath. And we used to go, how many times does 5 go into 7? Once. And then we do 1 times 5, that's 5. And then we subtract, we get 2. Bring down the 2, and then we would repeat that process. How many times does 5 go into 22? 4. 4 times 5 is 20. Subtract, we get 2, and then we'd bring down that 3. How many times does 5 go into 23? 4 times 5 is 20. Subtract, we get 3, and we would write a remainder of 3. Now we're probably thinking, oh great, this is what we're doing. That's awesome. I know how to do this. Not quite. This is just an introduction to kind of get your mind thinking back on those steps we took. Because like I said, when we start using polynomials instead of these constants, we're going to take those exact same steps. Now we're going to look at one more example with using numbers. 1,278 divided by 6. We're going to set it up. 1, 2, 7, 8. Now in this one, we know we're actually going to start with the 12. But before we used to say, how many times does 6 go into 12? What we're really doing is we are dividing 12 by 6. Now, oftentimes it doesn't divide evenly, but sometimes it does, like in this case. But what I want you guys to do is emphasize on changing the language in your head. Rather than saying, how many times does 6 go into 12, I want you thinking of it as 12 divided by 6. This is going to be crucial in helping us divide polynomials. So 12 divided by 6 is 2. 2 times 6 is 12. We subtract, we get 0, and we bring down the 7. 7 divided by 6 is 1 with some left over, right? But it's still 1. 1 times 6 is 6. We subtract, we get 1. We bring down the 8. 18 divided by 6 is 3. 3 times 6 is 18. We subtract and we get 0. Now we're done. Our remainder was 0. What does that mean when we get a remainder of 0? That means that 6 is a factor of 1,278. It also means that the 213 is a factor of 1278. Because 6 divided evenly, it means it's a factor, and what we ended up, our quotient, 213, is the other factor. Thinking ahead, what this opens up the door for us is another way to factor polynomials. X squared plus 14x plus 45 divided by x plus 9. We're dividing by x plus 9, so that's going to go on the outside. And we are dividing x squared plus 14x plus 45. Now we always start with the very first term, and we're starting with the first term in our divisor. X squared divided by x. Remember when I told you guys to change the language? This is why. And a lot of times we'll come to our margin and set that up. What is x squared divided by x? That is x. Now when I multiply x times x plus 9, I get x squared plus 9x. Again, I'm doing the exact same steps I did before. I started with dividing x squared divided by x, and then I multiplied my value up here times my divisor. The only difference is that now we're getting a binomial. Now the next step is to subtract, but I'm subtracting all of this. So when I draw my subtraction sign, I'm also going to draw parentheses to indicate that I'm going to distribute that negative. X squared minus x squared is 0. 14x minus 9x is 5x. We bring down the 45 and we continue using that exact same sequence. Again, we're starting with the first term, 5x divided by x. If I set that up in my margin as a fraction, it's easy to see how that divides. 5x divided by x is 5. 5 times x plus 9 is 5x plus 45. And my next step is to subtract. And when I draw that subtraction sign, I'm also going to add my parentheses so I remember to distribute that negative. 5x minus 5x is 0. 45 minus 45 is 0. I have a remainder of 0. So my answer, my quotient is x plus 5. Now, taking this one step further, because I had a remainder of 0, that means that x plus 9 is a factor of that quadratic. It also tells me that my other factor is x plus 5. So if I look up here, x squared plus 14x plus 45, let's just try to factor this. We know since the lead coefficient is 1, I can start with my binomials leading with x. Factors of 45 that sum to 14. That's going to be positive 9 and positive 5, which are these two values. If you can see where my cursor is, my two values here, or expressions there. Again, the purpose of this exercise was just to divide, so my answer was x plus 5, but I'm trying to get you guys to see the connection between this division and factoring, which we've already seen. 7 minus 11x minus 3x squared plus 2x cubed divided by x minus 3. First observation I have is that this polynomial right here is not in the right order. So I'm going to rewrite it so that it's in standard form. That means having my exponents in decreasing order. So this is 2x cubed minus 3x squared minus 11x plus 7. Divided by x minus 3. X minus 3 goes on the outside of my division bar. And now we start the long division. 2x cubed divided by x. I'm going to set that up in my margin. 2x cubed divided by x. If you were to simplify that fraction, you get 2x squared. Now I'm going to pause here for just a second. If you noticed in the last example, I'm lining up my like terms. It's not essential that you do that. I just do that because I like things to be organized. But it's not necessary. It just is set up so that they're lined up with their like terms. So we have 2x squared times x minus 3. 2x squared times x is 2x cubed. 2x squared times negative 3 is negative 6x squared. Now I have to subtract the entire thing, so when I draw my subtraction, I'm also going to add my parentheses so I remember to distribute. 2x cubed minus 2x cubed is 0. Negative 3x squared plus 6x squared is positive 3x squared. We bring down minus 11x and we repeat the same steps. Starting with 3x squared divided by x. Again, I'm going to set that fraction up in my margin just so that I can see the division a little bit easier. 3x squared divided by x is going to be 3x. 3x times x minus 3. 3x times x is 3x squared. 3x times negative 3 is negative 9x. I'm subtracting this entire thing, so I add parentheses. 3x squared minus 3x squared is 0. Negative 11x plus 9x is negative 2x. Bring down the plus 7 and repeat. Negative 2x divided by x. That simplifies to negative 2. And I take that negative 2 and I multiply it by x minus 3. Negative 2 times x, negative 2x. Negative 2 times negative 3 is positive 6. I'm subtracting the entire thing, so I'm adding my parentheses to remember to distribute that negative. Negative 2x plus 2x is 0. 7 minus 6 is 1. And we can see that 1 is not divisible by x. So this represents my remainder. Now, before we used to write remainder 1. But we've all grown up from that. We no longer write it like that. Now we write it as what we are trying to represent. We're trying to divide 1 by something. That something is x minus 3. So we're going to add that fraction of 1 divided by x minus 3, which we cannot divide any further. And this represents our quotient, the entire answer when we divide. One of the things that you probably noticed, and I tried to emphasize it, was I'm subtracting the whole thing, so make sure you add parentheses. I'm subtracting the whole thing, so make sure you add parentheses. Subtracting the whole thing, make sure you add parentheses. That's really important, folks. We have to distribute that negative sign. If you don't include the parentheses, there's a chance that you won't. So those parentheses will help be that reminder to distribute that negative throughout the two pieces. 2x to the fourth plus 3x cubed minus 7x minus 10 divided by x squared minus 2x. Take a look at this polynomial. Is there anything missing? Well, if we go down, we've got x to the fourth, x cubed, and then we've got an x. We're missing an x squared term. When we're dividing, we want to make sure that we use placeholders for any terms that we're missing. So this is the same as 2x to the fourth plus 3x cubed minus 7x minus 10. And we're going to put something here to hold the place of my x squareds. But I can't just add something to this polynomial, otherwise it changes the polynomial. So what can I put there that doesn't change the polynomial but gives me that placeholder? 0x squared. 0 times x squared is still 0, so we're not changing the expression, but we are giving a value for x squared. All right, so we set it up. X squared minus 2x goes on the outside. 2x to the fourth plus 3x cubed plus our placeholder 0x squared minus 7x minus 10. Divide as we would. 2x to the fourth divided by x squared. Again, using my margin to help me simplify these. 2x to the fourth divided by x squared is 2x squared. If you guys remember what I said before, I'm already happy I've got this placeholder because now I've got a like term to line it up with. Before I didn't have an x squared. We multiply 2x squared by x squared minus 2x. 2x squared times x squared is 2x to the fourth. 2x squared times negative 2x is negative 4x cubed. I'm subtracting the whole thing, so I make sure I add my parentheses. 2x to the fourth minus 2x to the fourth is 0. 3x cubed plus 4x cubed is 7x cubed. And then I bring down my 0x squared. And I repeat, 7x cubed divided by x squared. Going to my margin to set up that fraction, 7x cubed divided by x squared is going to be 7x. 7x multiplied by x squared minus 2x. 7x times x squared is 7x cubed. 7x times negative 2x, negative 14x squared. I'm subtracting the whole thing, so I'm including parentheses to remember to distribute. And now I've got 7x cubed minus 7x cubed is 0. 0x squared plus 14x squared is 14x squared. Now I'm going to pause here and just show you one more reason why we want to make sure we have the placeholder. If I didn't have this placeholder of x squared, this term right here, if you can see what I'm circling, would actually be a negative 7x. And if I had negative 7x plus 14x squared, a lot of times I'm not going to recognize that those are not like terms, and I'm going to try to combine them anyway. So again, we want to use that placeholder so that in the event we have to combine it with another like term, we actually have something to combine it with. So now we're going to bring down that negative 7x, and we repeat those steps. 14x squared divided by x squared. Using my margin, 14x squared divided by x squared is 14. 14 times x squared minus 2x. 14 times x squared is 14x squared. 14 times negative 2x is negative 28x. I'm subtracting the whole thing, so I'm going to use parentheses to remember to distribute. And hopefully you remember the sound of my voice when you are doing this on your own at home. 14x squared minus 14x squared is 0. Negative 7x plus 28x is 21x. Bring down the minus 10. And now we try to repeat the same thing. 21x divided by x squared. Now if we set this up, is this going to divide evenly? In other words, when we simplify this, do we get rid of the fraction? And in this case, we can't. We can cross out 1x here and 1x here, but then that's left with 21 over x. So it no longer divides evenly, which means this represents my remainder. If you guys remember, we no longer write remainders with the capital R. Now we write it as a rational expression. This is 21x minus 10 divided by x squared minus 2x. And this is our entire answer when we divide. It's called the quotient. Yeesh, that's a long problem, isn't it? So we just saw several examples using long division. We want to make sure our polynomials are in order from are in standard order, standard form, so our exponents are decreasing, and we need to use placeholders. And we also saw that they can be very, very long and time consuming. There is another form of division called synthetic division. Now, synthetic division is super awesome. You're going to love it. But the drawback with synthetic division is you can't use it all the time. You can only use synthetic division when you're dividing by x minus c. X minus c is going to look like this, x plus 3. I call it my naked x. If I look at my divisor, as long as there's no coefficients on x and there's no exponents on x, so your x is naked, then you can use synthetic division. So if you recall from your lecture video, when we're setting up for synthetic division, we have our little box that we put our value of c. Now, if you're looking at your divisor, this value right here is going to help you identify c, but it's always going to be the opposite of this value. So it's going to be negative 3 in this problem. Next, we list out our coefficients from our dividend. 5, negative 12, negative 8. We always start by bringing down the 5. Then we multiply 5 times negative 3 is negative 15. And then we add vertically. Negative 12 minus 15 is negative 27. And we repeat, negative 27 times negative 3 is positive 81. Positive 81 plus negative 8, 73. That was really fast, and I was even having to check my notes. But you guys have a calculator real handy. But let's look at what these values represent. This 73, or the rightmost value, is always your remainder. And then these numbers become the coefficients of your quotient, of your answer. So if I started with 5x squared and I divided by x, 5x squared divided by x is going to give me 5x. Then we've got minus 27 plus our remainder was 73 over x plus 3. The thing to remember when setting up your quotient, again, we use these two numbers as our coefficients. We're always starting with a variable exponent 1 less than our original dividend. So if I started with x squared, my answer starts with x. If I started with x cubed, my answer will start with x squared, so on and so forth. Okay, let's try one more. X cubed minus 7x minus 6 divided by x plus 2. My dividend, or excuse me, my divisor checks out. I can use synthetic division because, again, I've got that naked x. My c, I can tell, is going to be negative 2. Again, I'm using the opposite when it's attached to x. But when I look at my dividend, the x cubed minus 7x minus 6, it looks like it's missing some pieces. Just like in that previous example when we were using long division and we had to use placeholders, you have to do the same thing for synthetic division. So if I rewrite this, this is x cubed. I don't have an x squared, so I'm going to add 0x squared for a placeholder minus 7x minus 6 divided by x plus 2. In our half box goes c, which is negative 2. And then to the right of that, we state our coefficients. Our coefficients are 1, 0, negative 7, negative 6. In synthetic division, you absolutely need to make sure you have your placeholders, otherwise it won't work out correctly. So we bring down the 1. 1 times negative 2 is negative 2, plus 0 is negative 2. Negative 2 times negative 2 is 4. Negative 7 plus 4 is negative 3. Negative 3 times negative 2 is positive 6. And negative 6 plus 6 is 0. So in that example, it was very quick and easy to do that arithmetic. The 0 represents our remainder, which means it's divided evenly. And our answer, the lead coefficient, is going to be 1. And since I started with x cubed, my answer starts with x squared. So we've got 1x squared minus 2x minus 3, and a remainder of 0. So we're done. Much faster, guys. If you don't believe me, I suggest that you try to work this division problem out using long division. 4x squared minus 3x plus 6x to the 5th minus 2x cubed plus 1 divided by x minus 2. The first thing I want to check, can I use synthetic division? Absolutely, I've got that naked x. And c is equal to positive 2. Now let's look at our dividend. 4x squared minus 3x plus 6x to the 5th plus 2x cubed plus 1. This is very unorganized, so we want to start by writing this in standard form. 6x to the 5th is the highest exponent, so we'll start there. X to the 4th. I don't have an x to the 4th term, so I'm going to use my placeholder. Minus 2x cubed. X squared, we've got plus 4x squared minus 3x plus 1. All right, so we set up our half box. We put in there c, which is 2, and then we list our coefficients. 6, 0, negative 2, 4, negative 3, 1. Just envision all of the rows that you would have if you were using long division. Synthetic division is our friend and we love it. We bring down the first coefficient always. It's not sometimes, always we bring down our first coefficient. 6 times 2 is 12, plus 0 is 12. 12 times 2 is 24. Plus negative 2 is 22. 22 times 2 is 44. 44 plus 4 is 48. 48 times 2 is 96. Plus negative 3 is 93. 93 times 2 is 186, plus 1 is 187. Now, in my years of doing math problems, I've gotten very good at this mental math. Some of you guys might be just a hair slower, and you might be grabbing your calculators. That's perfectly fine, okay? Just make sure that you're getting the same values that I am, even if you might be a few seconds behind. The 187 is our remainder, and all of these other numbers are the coefficients of our quotient. Now, we started with x to the 5th, which means our answer will start with x to the 4th. So we have 6x to the 4th plus 12x cubed plus 22x squared plus 48x plus 93 plus 187 over x minus 2. A very long answer for an otherwise very quick problem. That's why we like synthetic division so much. It's very, very quick to use. Use the remainder theorem to evaluate f of c for the given value of c. A remainder theorem is one of the applications for synthetic division. Basically, it says that if I take my function f of x and I divide it by x minus c, this is my c, then the remainder, hence remainder theorem, the remainder is equal to f of c. So to summarize, f of negative 4 is going to equal the remainder. So I need to find that remainder using synthetic division. So inside my box for synthetic division, we put our c, negative 4. Now notice I didn't change the sign here because this value given was c. Only when the constant is attached to x, like in that the divisor x minus 2, x plus 3, do you change the sign. So we place c and then we list out our coefficients. 3, 4, negative 5, 3. If I needed a placeholder, I would have used one. We bring down the first coefficient. 3 times negative 4, negative 12. 4 plus negative 12, negative 8. Negative 8 times negative 4, positive 32. 32 plus negative 5 is 27. 27 times 4, negative 108. And negative 108 plus 3 is negative 105. Now, again, going back to the directions, they want us to evaluate f of c. F of c, c was negative 4, is equal to the remainder. What's our remainder? Negative 105. Now, many of us might be looking at this or thinking, why not just plug negative 4 in for x? So I've got f of negative 4 equals 3 times negative 4 cubed plus 4 times negative 4 squared. I'm already bored with writing that down. You can do it that way, it will work, but this synthetic division, although it seems like it takes up more space, is actually much easier. All we're doing is multiplying and adding. That's it. With that said, let me make this perfectly clear. On your exam, you're going to have a question that says, use the remainder theorem to evaluate f of c. If I'm telling you to use the remainder theorem, I expect you to use the synthetic division and what the remainder theorem states in order to find your answer. Now, if you want to double check it using this method of just plugging it into the function, that's fine, but I'm going to be looking for this synthetic division. When I see the synthetic division, that communicates to me, you know what the remainder theorem says. So it's not optional in this case. A lot of times I'm pretty flexible with how you choose to solve a problem, but in this case, since I'm asking you to use a specific method, you have to use it. So just to recap, we looked at long division and synthetic division. Long division, nice because we've already done it before, so we have some previous knowledge on how to divide using long division. Synthetic division, nice because it's super quick. However, remember, you cannot always use synthetic division, so you need to make sure that you can identify when you can and cannot use synthetic division. Before we cut off, I'm just going to scroll back through some of these examples that we use long division for, and let's determine whether or not we can use synthetic division. So in this example, could you have used synthetic division? Yes. In this example, could you have used synthetic division? Yes, you could have because of the, again, naked x. But if I look at this example, I was dividing by x squared minus 2x. I cannot use synthetic division here because my x has an exponent, but then I also have another x that has a coefficient. So make sure you guys are confident in identifying when you can use either technique. And then we saw an application of synthetic division, and that's the remainder theorem, which is a nice handy way of evaluating a function. In our next video, we will wrap up our conversation on rational functions with solving rational equations. So we'll see you next time. Thank you.